Good morning, everyone. I'll be presenting my thesis defense here on the topic accelerating the evaluation of large workloads on post-Dennard systems with sampling. This is basically a culmination of all the work that I have done for the last 6 years during the PhD with Professor Trevor Carlson. And it primarily focuses on developing techniques, novel techniques to accelerate the performance evaluation of large workloads on these modern systems. These days, the modern hardware design metric, what people care about are three different things. One is power, one is performance, and one is area. So we basically want the power and the area to go down and the performance to go up. So this is usually the case that we expect. And yeah, if you see the trend over the last 30 years, you could see that the performance is definitely improving, but you can observe like after 2005 or so, the performance improvement is kind of linear, but until then it's more like exponential. So I'll explain the reason later on in the presentation. One of the key laws that drive computer architecture research, or that used to drive computer architecture research until the past few years, is Moore's law. Moore's law states that the number of transistors on chip doubles every 18 months. It's not really a law per se. It's not a physical law or anything. It's like an observation that Gordon Moore made in 1965. And this figure is from the paper from Gordon Moore at that time, where he observed that the number of transistors on chip doubles every almost 2 years. And the observation held true until recently, until like the early 2000s, until traditional node scaling reached its limits. So why does traditional node scaling reach the limits? It's because of nature's law, like physical limits. You can say it's more similar to Heisenberg's uncertainty principle, and this is on the background, that's what you're seeing, the derivation of Heisenberg uncertainty principle. This resulted in CPUs having clock frequencies like going linear after a point. Like if you observe from 2005, you can see the CPU frequencies are going linear rather than like going exponential as we observed before 2005 or so. So this is the implication of Moore's law, and this is the part where the processor frequencies no more increase over time because we reach the physical limits of Moore's law. A similar law to Moore's law is Dennard's law, where Dennard's law says that the performance per watt of computing doubles every 18 months. But this law also broke because of Powerwall, which is again similar to like how Moore's law broke. So we cannot improve the performance per watt of a chip by reducing the size of it. At this point, what we need is some solution to improve the performance of modern hardware. And how do we do this? So one of the solutions that people come up with is multi-core architectures or multi-core CPUs, where multiple processing units work together to solve problems. So another solution is to have specialized hardware like GPUs, TPUs, NPUs, etc., like accelerators to improve the performance of particular class of workloads. And another example would be heterogeneous systems where multiple computing units interconnected closely together to form a heterogeneous system where these computing units work together. So you see the architectures in post-Dennard era are much complicated than it was while Moore's law or Dennard's law was going fine. This is a figure from Intel, the recently released processor called Lunar Lake. This architecture basically combines CPU, GPU, NPUs, etc., into one die. So you can see how complicated these architectures are. And in order to evaluate the performance of these architectures, it requires much smarter techniques, like smarter in the sense that we cannot use the existing simulation techniques or performance evaluation techniques to analyze these kind of architectures. This is a graph that shows the simulation time taken for workloads like SPEC CP 2017, multi-threaded benchmarks, and SPEC HPC 2021, heterogeneous CPGP benchmarks. If you use detailed cycle level simulators like GEM5 for CPU or AccelSim for the GPU part, you could see that the whole workload simulation would take up to a century. Well, this is not acceptable, and you cannot wait for a century to evaluate certain workloads, but you need to evaluate those kind of workloads. So the question is, how do we bring down the simulation time? There are several techniques to accelerate the performance evaluation. And you can see these are the post-Dennard systems that I have shown before. And these days, people use several techniques to accelerate the performance evaluation, like sample simulation or analytical models or developing synthetic benchmarks. What is sample simulation? Sample simulation is basically identifying a sample within a large workload, which could be simulated so that the performance of the whole workload on the system can be extrapolated. Analytical models are basically models that are mathematical or statistical, which could be used to estimate the performance of one fixed system for a workload. This would be quick, but it would not be accurate because it's not deeper enough, like simulation. And also, you need specific models for each kind of hard architecture. In the case of synthetic benchmark, generating new small benchmarks based on very large benchmarks. The problem with these techniques is that it may not represent a big cache hierarchy or something for large workloads. So we would not see the impact of the workloads on this hardware. So synthetic benchmarks and analytical models are kind of inaccurate, and we probably would like to move ahead in the direction of sample simulation. All right, so let's talk a little on the current performance estimation landscape. That's the related work. The first work on sample simulation, as we currently acknowledge, is SimPoint, which was published in 2002, where methodology is applicable to single-threaded workloads. And at that time, that's the general kind of workloads available. And another technique that was proposed in 2003 was SMARTS, again, using 4 single-threaded applications. And both of these techniques use instruction counts as the unit of work. Like they assume the instruction counts would not vary across executions of one particular application. And then comes a few multi-threaded sample simulation techniques. First one proposed was SimFlex, which is proposed in 2006. It's an extension of SMARTS, but the problem is that it applies only to multi-threaded workloads that don't synchronize, so basically like the throughput workloads. So in this era, we need techniques that can evaluate synchronizing multi-threaded workloads. And the first one proposed that was time-based sampling, and that was proposed in 2013, I guess. Time-based sampling was a methodology that, in fact, revolutionized multi-threaded sampling because it's the first of a kind sampling technique at that time, where time is used as a sampling unit. Later, barrier point was proposed, but the problem with barrier point is that barrier point is applicable only to those applications that are synchronized by barriers. Barriers are synchronization units. And then task point comes, where task point is applicable only to task-based applications. These two are not generic, but time-based sampling is applicable to generic multi-threaded workloads. The problem with time-based sampling is that it's extremely slow. You probably would not get the benefit that you expect from sample simulation using time-based sampling. And there are other techniques like analytical models proposed during that time, like interval model or roofline or MPPM, and then later RPPM. This all came, and like I said before, analytical models are something that we are not considering in this thesis, and we would not go ahead in that direction because of accuracy issues. And there are like other workload reduction techniques like MAMPO, synchrotrace, and Ditto for CPU workloads. So in this space, you can see the gap here, right? The problem is we do not have a generic methodology that is quick to evaluate, and the overall turnaround time is within a few hours. So to that end, we propose LoopPoint, where we identify representative regions of multi-threaded applications, and then we are able to simulate them in parallel and get the results in a few hours. So loop point fits right there. And the problem with loop point is that loop point is not applicable to dynamically scheduled multi-threaded workloads. Although it's generically applicable, we do not assume loop point would work for dynamically scheduled applications because loop point depends on the profile of a workload and it reuses the profile. So the assumption is that the profiled by loop point will not change over multiple executions. That's not true in the case of dynamically scheduled software or hardware. So on that front, we propose PAXM, where PAXM analyzes the workload online while it is being simulated, so that it doesn't matter. We don't need to profile an application. We don't need to keep checkpoints. It's all online. So that is what PAXM does. And with PAXM, we assume that we are solving the problems of multi-threaded sampling. And the next kind of workloads are accelerator workloads. And there are a few techniques available here, like TV point, PKA, principal kernel analysis, Steve, Photon. Photon was proposed by our group, and currently it's the best technique available for sampling GPU workloads. I'm not going into details on GPU sampling techniques because those problems I feel are addressed in Photon, and I'm not going ahead with that. There are a few analytical models also proposed. So you can see that the first analytical model for GPUs came in 2009, I guess, workflow graph. And then GPU Perf, GPU Mech, all this came from Georgia Tech and UT Austin. Aladdin from Howard, and also sparse loop. Aladdin and sparse loop are analytical models of accelerators. You could see that this kind of space is quite addressed well, in the sense that although sample simulation of accelerators is still an open issue, this still takes time because the kind of accelerator workloads are extremely diverse, and it's hard to do such kind of sample simulation methodologies. So we also have some workload reduction techniques. Right. The next kind of architectures are heterogeneous architectures, where we do not see any sort of methodologies to address heterogeneous workloads until 2020 or something, where GABLES was proposed and FFM was proposed. Those are analytical modeling techniques. One problem with heterogeneous systems is that you don't have several simulators to evaluate them. And whatever existing is Gem5 or Gem5 GPU, those are extremely slow. What people do is to develop analytical models for this so that it's much easier to evaluate them, although the accuracy is not good enough. There's another workload reduction techniques from MIT, that's Mystic. It is similar to Ditto from the same group. It's applicable to heterogeneous workloads. So to this end, we propose XP point, where we propose sample simulation technique for heterogeneous CPU GPU workloads. So it's the first of its kind in this space of workloads or systems. So XP point, it's under review currently, but still once it is proposed, it's the first sample simulation technique proposed for heterogeneous CPU GPU workloads. So the relevant publications during PhD are here. I'll be selecting only 3 of these to present here. And there are a few workshops, conferences, and some work in progress as well. All right, so let's get started with the first technique that I want to discuss today. That's loop point. Loop point was published in HPCA in 2022, and it was done in collaboration with folks from Intel Corporation, Harish Patil and Bim Herman. I really acknowledge their help in coming up with this technique. All right, why do we need to come up with this methodology? Like I said before, there are a few multi-threaded sample simulation techniques, but those are either slow or are applicable only to specific class of workloads. So we wanted to develop a methodology that is applicable to generic multi-threaded workloads. Apart from that, there are a few other complications with respect to multi-threaded workloads. For multi-threaded workloads, you cannot use instruction count-based techniques like SimPoint or smarts. Basically, you cannot extend SimPoint or smarts for multi-threaded workloads because the instruction counts or multiple runs will vary for multi-threaded applications because of presence of spin loops or other synchronization instructions. And for multi-thread applications, threads progress differently. Could be due to several reasons and also due to load imbalance on the hardware. And another problem with multi-threaded sample simulation is to represent parallelism among the threads. So you know that the threads may not be doing equal amount of work all the time. So we need to somehow represent the parallelism among the threads. Also, we need to differentiate thread weighting from real work, that is the synchronization. We don't need to count synchronization into the real work done because it's not real work, and it varies from system to system. We want to ignore them. So in order to address all these problems, we came up with a unit of work that is program loops. Program loops are ubiquitous in the program, and it's available in plenty in typical CPU workloads. So we will use program loops as a unit of work to devise loop point sample simulation technique. A high-level idea of how loop point works is that assume we are in a program execution and we have several loops within the application. And at any point, the profiler identifies the beginning of a loop as the beginning of a region, and it waits until a threshold number of instructions to start identifying the end of the region. And we end the region at the end or beginning of another loop. So in this sense, we will not have repeatability issues. That means we can repeat the same region over and over because it's based on loops and it's based on loop counts. And this region could be represented using the program counter and the particular count at the particular point of the loop. So from this region, assume this is some n plus 1 threaded region. And from this region, you get basic block vectors for each thread. And what are basic block vectors? So basic block vectors are essentially the execution fingerprint of an application for a particular interval. So this is an example of a basic block vector where you have the basic block IDs, and those are the instructions of one particular basic block. And basic block ends at a branch. So in one basic block, you will not encounter a branch. And a basic block vector is when you take the basic block ID and multiply it by the number of times you saw the basic block and the number of instructions. So basically here there are 8 instructions in basic block 1, and you saw the basic block 1 only once in an execution. So the count is 8. 8 times the number of occurrences, that's 1. In the next one, the basic block 2, the number of instructions in the basic block is 3. And assume you encounter that basic block 20 times. So that is 20 times 3, that is 60 there. So that's the basic block count there. So this is how you construct the basic block vector. And assume this is for thread 0. And for thread n, we have a different basic block count. And now what we need to generate is a vector that could represent the parallelism of multi-thread application. In order to represent the whole multi-threaded region, we need to concatenate all the basic block vectors together to form a larger concatenated global basic block vector. So this is how we do it. We first add the thread 0's basic block vector and then modify the basic block ID of the upcoming thread IDs like this. For example, W is a basic block ID of thread n. So we multiply n with the max BBB, max basic block that we encountered, and add it with the basic block ID of the particular thread, just to make it unique. So that's the concatenation part of it. We cluster the entire space of basic block vectors and then identify the representative regions. Here we have the sampling errors using loop point while estimating the simulation runtime of spec CPU 2017 benchmarks that use active wait policy. So active wait policy is a policy when OpenMP threads are running in spin loops while they synchronize. And the errors for passive wait policy, where passive wait policy means that the threads may go to sleep or go to the kernel mode. It will not consume CPU cycles in the user mode. Using loop point, we get an average error of around 2.3% overall for spec CPU 2017 benchmarks. These are the errors and what we gain from this, like the simulation time reduction. We can see that detailed simulation of these benchmarks like NPB or spec benchmarks with large inputs could take more than a year, even using techniques like time-based sampling or barrier point. Even using barrier point, you get for spec ref inputs, you may not get the complete results within a month or so. In this case, yeah, there's definitely a need for a technique like loop point. That's where loop point comes into picture, where we get all the simulation results in a few hours. This is primarily enabled by the parallel sample simulation that loop point allows. So basically, we get the simulation results in a few hours rather than waiting for months or years. That's about loop point, where we present a sample simulation technique using loop-based regions. We are able to simulate multi-thread applications in a few hours instead of years. And the work was published in HPCA, and we conducted several tutorials at ISPAS, ISCA, HPCA, etc. The technique is integrated with Sniper and Jumpfire, and we have released several loop point-based checkpoints for spec benchmarks for people to use. Problems that I mentioned earlier about loop point was that loop point is unable to address any dynamic schedules or dynamic changes within the application or the hardware. So in order to address this problem, we are presenting PAXM, which is using live profiling, live sampling in order to address the dynamism within the application. As we know, modern hardware is not at all static because of several things happening like DVFS, turbo boost, cache reconfigurations, etc. Is the software any different? No. Software is also dynamic, heavily dynamic these days. You can see the OpenMP dynamic schedule here, where each loop iteration, these are loop iterations, and it could be mapped to different cores in different runs. So this basically means that it invalidates any profiling-based sampling techniques. So you cannot keep one profile and use it again and again because the software is dynamic. The same applies to hardware as well. So in this kind of a scenario, what do we need is a sampling methodology that can adapt during runtime. That's what PAXM is about. And one of the primary motivations of PAXM is that this regions that we identified for FT benchmark within NPB. And you can see that the regions are clustered within 9 clusters, and the pattern repeats. Using this idea, we could simulate only a few regions in the beginning of the application and then probably fast forward until the end. This kind of technique can be developed when we have a dynamic sample simulation technique, like a technique that could evaluate and analyze an application online and then simulate it based on the runtime conditions. The red portions here are the regions simulated in detail. So here we present PAXM. We have several regions, and at some point of simulation, during the simulation of region R1, we are in the process of simulating and also detecting the endpoint of the region, that is a marker. And also we are profiling the region for an online BBV. So why do we need an online BBV? It's used for clustering so that the next region to be simulated in detail is made using the clustering results. All right, so once we detect the simulation mode using a predictor, then we decide whether the next region is to be simulated in detail or we just need to fast forward it. So this is how it works for all the regions. We saw online BBVs here. Those are used for clustering. And how we generate online BBVs is that we first have a basic block and then hash the PC and multiply it by the number of instructions of the basic block over D dimensions, where D is 16 here in our implementation. And this is accumulated within a BBV of that particular region. So for each basic block, we are accumulating into a region BBV. So this is the formula that if you are interested, basically accumulating all the individual basic blocks, BBVs, into a complete basic block vector. This happens in the Sniper front end. So while the backend simulation happens, this is happening in the front end. So a few sampling errors as compared to loop point and time-based sampling. You can see that these are like statically scheduled applications running 8 threads. You can see that the average errors are comparable with loop point, but it's better for PAXM. And speedups, we are comparing serial speedups here because PAXM's primary application is to simulate dynamically scheduled applications. And when we compare serial speedups, we obtain much higher speedups as compared to time-based sampling or loop point. Like I said before, the application of PACSIM comes when we simulate dynamically scheduled workloads. And we simulate these dynamically scheduled workloads from parsec and NPB using OMPSS and OpenMP. That's all about PACSIM. It's a fully online sample simulation technique that eliminates the need for profiling or application checkpointing. So this is the first sample simulation technique that could be applied to dynamically scheduled multi-threaded applications, as well as systems with dynamic hardware events. The paper was published at TACO, and we have open sourced the code that is integrated with Sniper. Until now, we have addressed all, at least tried to address all the problems with multi-threaded sampling. And next, we are moving to heterogeneous sampling with XPU point. The work is currently under submission, and it's done in collaboration with folks from Intel Corporation. Why do we need heterogeneous architectures in this era? It's because multi-cores aren't scaling well because of power and thermal constraints. And also, we talked about the ending of Dennard's law. The paper given here, dark silicon, that talks about the need to have dark silicon within a chip in order to have so many cores active at the same time. So in order to solve this problem, people came up with a different approach, which are like integrating different compute components together. And what we call that as XPU, where like CPU, GPU, NPU, etc., are all integrated closely together, and they share memory and synchronization primitives, etc. Some recent examples are like NVIDIA's Grace Hopper and I guess Apple's M series processors. Some of them do that. They closely connect CPU and GPU together with shared memory. However, this is the new thing, and like I showed before, we do not have several techniques to evaluate these. We have a few analytical models for estimating a rough performance, but that's not enough for these. What do? We need to simulate them, but the simulation slowdowns are extremely large, as we have seen before. CPU simulation are at least 10,000 times slower. And this is a very small number. Like I would say it's much, much slower than this. And GPU simulation, it's more like a realistic number. It's 1 billion times slow as compared to real execution. So these are kind of unacceptable and when it comes to heterogeneous systems, you can assume the slowdowns would be like heavy, much heavy. The graph shows that the simulation wall time for some benchmarks shown here, which are like spec HPC 2021 and some PyTorch inference runs, some of them will go up to a century. Of course, we will never live for a century to see the results. You can see that so most of the applications execute on native hardware within a minute or so. Again, these are like really new hardware. Basically, we cannot wait for a century for this kind of slowdowns in simulations. And we definitely need sample simulation. But the challenge here is that we do not have enough tools to support the co-analysis of CPU and GPU for developing any techniques for sample simulation. So here we come up with XPU pin, which basically integrates Intel's pin with several other instrumentation tools for GPUs. And currently we have integrated with GTPin and NVBit from Intel and NVIDIA. But it is possible to integrate several other instrumentation tools if they are available. These tools share callbacks so that pin tool is the main tool that interacts with the XPU pins infrastructure. And pin coordinates all the other instrumentation tools with callbacks. Using XPU pin, we build XPU profiler, where we use it to evaluate heterogeneous CPU GPU workloads. We see the future of XPU pin as a generic instrumentation framework, but we are not there yet. Using XPU profiler, I will show you how we do the sample simulation or sample selection. So we have heterogeneous CPU GPU workloads with all the shared libraries. We use XPU profiler and identify XPU BBB, similar to the multi-threaded BBBs we identified for loop point. And the difference here is that we demarcate the regions at the end of a kernel. We do this because we get repeatable regions over multiple executions. And an XPU BBB is a concatenated CPU GPU BBB, just a very long BBB with all the CPU and GPU execution fingerprints. This is clustered and fine-tuned. We get the weights with the corresponding regions of interest after clustering. And these regions of interest are simulated in detail in parallel. So this is basically the steps for sample simulation. XP profiler's region would look like this. So we have a heterogeneous workload where we have CPU code and GPU code. Not necessarily like this, but assume it's like this, a simple scenario. This is a slice that we consider, which consists of both CPU and GPU executions, and we end the slice at the end of a kernel here. The results, these are simulation results, what people like to see. These are simulated on Gem5 GPU, a heterogeneous CPU-GPU simulator that's available from 2012. We simulate only Rodinia benchmarks here because those are the shortest to simulate. And if you simulate any other benchmarks, it takes forever. So we simulated only Rodinia benchmarks and evaluated the sampling errors. Average error here is around 3%. And some of the errors are zero because you can see the number of regions identified are very few because the application is very short. We can simulate only small benchmarks, but when it comes to large PyTorch benchmarks, we cannot simulate them. So we validate them on native hardware. As I showed in the first graph, we cannot simulate these and wait for a century. So what we do is we evaluate them on real hardware and run just the samples and the full runs, extrapolate the sample performance, and then compare the full performance using native hardware. So this is done using hardware performance counters. So we get average errors using native hardware around 3.6% here. And the speedups are much higher than what we get from full detail simulation, obviously, because we are simulating only the samples, and we can simulate them in parallel. To summarize, we propose XPU point, which is the first CPU-GPU co-sampling methodology that's applicable to heterogeneous workloads. And in order to identify representative regions, we rely on kernel boundaries to demarcate regions. Current implementation of XPU point works with Intel and NVIDIA-based CPU-GPU platforms. And we expect it to be extensible to other heterogeneous platforms with accelerators and stuff. And the work is under review. We will open source the tools upon acceptance. And that's all about the PhD.